What if the universe holds secrets so profound that even the brightest minds can only scratch the surface? Imagine a place where gravity is so intense that not even light can escape, where time itself bends and warps, and where the very fabric of reality unravels. This is the realm of black holes and singularities, cosmic enigmas that defy our understanding of physics and challenge the limits of human imagination. For decades, scientists have peered into the depths of space, unraveling mysteries and uncovering clues, yet black holes remain one of the most perplexing phenomena in the universe. What lies beyond the event horizon? Can anything escape their grasp? And what happens at the heart of a singularity, where the laws of physics as we know them cease to exist? In this video, we'll dive into 30 of the most mind-bending unsolved mysteries surrounding black holes and singularities. From the fate of matter falling into these cosmic voids to the possibility of wormholes and alternate universes, prepare to explore the unknown. Stay with us, because by the end of this journey, you'll not only uncover the secrets of these celestial giants, but also glimpse the cutting-edge theories that could redefine our understanding of the cosmos. Let's begin. Now, as we venture deeper into the mysteries of black holes, let's turn our attention to the first and perhaps most baffling question: what happens inside a black hole? Beyond the event horizon, the boundary where even light cannot escape, lies a realm where the rules of physics as we know them begin to crumble. Imagine a place where space-time is so warped that it folds in on itself, creating a gravitational pull so intense that nothing, not even information, can break free. This is the heart of the black hole, a region where the concept of space and time as we understand them ceases to exist. At the center of this cosmic abyss lies the singularity, a point of infinite density where matter is compressed into an unimaginably small space. Here, the equations of general relativity break down, and our current understanding of physics hits a wall. The singularity represents a place where the laws of nature as we know them no longer apply, leaving scientists with more questions than answers. One of the greatest challenges in studying what happens inside a black hole is the fact that no information can escape from beyond the event horizon. This means that, from our perspective outside the black hole, the interior remains forever hidden, shrouded in mystery. Theories abound, from the idea that black holes might contain entire universes within them to the possibility that they could serve as gateways to other dimensions. Yet, without the ability to observe or measure what lies within, these ideas remain speculative. The enigma of what happens inside a black hole is not just a question of curiosity, it's a fundamental challenge to our understanding of the universe itself. As we continue to explore, we're left to wonder, will we ever truly know what lies beyond the event horizon, or will the secrets of the black hole remain forever out of reach? Now, as we shift our focus to another profound mystery, let's explore the question, do black holes destroy information? This puzzle lies at the heart of one of the most significant conflicts in modern physics, the information paradox. At its core, this paradox pits two of our most successful scientific theories against each other: quantum mechanics and general relativity. Quantum mechanics tells us that information about the state of a system can never be truly lost. It might change form, but it's always preserved in some way. Yet, when it comes to black holes, general relativity seems to suggest the opposite. When matter falls into a black hole, it appears to vanish completely, taking all its information with it. This creates a glaring contradiction, as the laws of quantum mechanics insist that information must be conserved, while black holes seem to defy this principle. The debate over this paradox was ignited in the 1970s by the groundbreaking work of Stephen Hawking. He proposed that black holes aren't entirely black. They emit a faint radiation, now known as Hawking radiation, which causes them to slowly lose mass and eventually evaporate. But here's the catch: Hawking radiation appears to carry no information about the matter that originally fell into the black hole. If this is true, it would mean that the information about that matter is irretrievably lost, violating a fundamental tenet of quantum mechanics. This idea sent shockwaves through the scientific community, sparking decades of intense debate and research. Some physicists argue that the information isn't truly lost but is somehow encoded in the Hawking radiation, though we don't yet understand how. Others suggest that the information might be stored in a hidden structure near the event horizon, or even that it escapes into another universe. Then there are those who propose that our understanding of black holes is incomplete and that a unified theory of quantum gravity, one that reconciles quantum mechanics and general relativity, might hold the key to resolving the paradox. Despite the many theories, a definitive answer remains elusive, leaving the fate of information in black holes one of the most tantalizing unsolved mysteries in physics. As we ponder this enigma, it's worth considering the broader implications. If information can indeed be lost in black holes, it would force us to rethink some of the most fundamental principles of physics. On the other hand, if information is preserved, it could reveal entirely new insights into the nature of spacetime and the universe itself. The information paradox isn't just a theoretical curiosity, it's a gateway to deeper questions about the fabric of reality. And as we continue to explore, we're left to wonder, will we ever uncover the truth about what happens to information in the depths of a black hole? Now, as we venture deeper into the enigmatic world of black holes, we arrive at a question that challenges the very foundations of our understanding. What is the true nature of singularities? At the heart of every black hole lies a singularity, a point where the laws of physics as we know them cease to function. Here, density becomes infinite, space-time curves beyond comprehension, and our current theories break down entirely. It's a place where the familiar rules of the universe no longer apply, and yet it's a concept that general relativity insists must exist. According to Einstein's theory, when a massive star collapses under its own gravity, it forms a black hole with a singularity at its core. This singularity is a region where matter is crushed to an infinitely small point, and the curvature of spacetime becomes infinite. But here's the problem. While general relativity predicts the existence of singularities, it fails to describe what actually happens there. The equations simply stop working, leaving us with a mathematical and conceptual void. It's as if the universe itself is telling us, this far and no further. This breakdown isn't just a technical glitch, it's a sign that our understanding of gravity and spacetime is incomplete. To truly grasp the nature of singularities, we need a theory that unites general relativity with quantum mechanics, the framework that governs the behavior of particles at the smallest scales. Quantum gravity, a still elusive theory, is widely believed to hold the key. It could potentially reveal what happens when infinite density meets the quantum realm, where particles behave in strange and unpredictable ways. Some theories suggest that singularities might not be points of infinite density at all, but rather regions where quantum effects smooth out the extreme curvature of spacetime. Others propose that singularities could be gateways to entirely new dimensions or even other universes. Yet, without a complete theory of quantum gravity, these ideas remain speculative. The true nature of singularities remains one of the most profound mysteries in physics, a puzzle that continues to challenge and inspire scientists around the world. As we contemplate the singularity, we're reminded of the limits of human knowledge. It's a humbling thought that, despite our incredible advancements, there are still phenomena in the universe that defy explanation. But it's also an exciting frontier, one that promises to reshape our understanding of reality itself. What lies at the center of a black hole? What secrets does the singularity hold? For now, these questions remain unanswered, beckoning us to explore further into the unknown. Now, shifting our gaze to another perplexing question, we ask, can anything escape a black hole? For decades, the answer seemed straightforward. Nothing, not even light, can break free from a black hole's immense gravitational pull once it crosses the event horizon. This idea has been a cornerstone of our understanding of these cosmic giants. But as with many mysteries in the universe, the story doesn't end there. Enter Hawking radiation, a groundbreaking concept proposed by physicist Stephen Hawking that challenges this very notion. Hawking radiation suggests that black holes aren't entirely black after all. Near the event horizon, quantum effects come into play, creating pairs of particles and antiparticles. Normally, these pairs annihilate each other almost instantly. But in the extreme environment near a black hole, one particle can fall into the black hole while the other escapes, carrying away a tiny amount of energy. Over time, this process causes the black hole to lose mass and eventually evaporate. It's a slow, almost imperceptible process, but it fundamentally changes our understanding of black holes. This discovery raises profound questions. How exactly does Hawking radiation work at the quantum level? What happens to the information carried by the particles that fall into the black hole? And if black holes can evaporate, what does that mean for the fate of the matter and energy they've consumed? These questions remain unresolved, sparking intense debate among physicists. Some argue that the information is lost forever, violating the principles of quantum mechanics, while others believe it might be encoded in the radiation itself. The implications of Hawking radiation are staggering. If black holes can evaporate, it suggests they have a finite lifespan, challenging the idea that they are eternal cosmic traps. It also opens the door to new theories about the nature of spacetime and the interplay between quantum mechanics and gravity. Yet, despite decades of research, we still lack a complete understanding of this phenomenon. The mystery of what truly escapes a black hole and what it means for the universe remains one of the most tantalizing puzzles in modern physics. As we ponder these questions, we're reminded once again of the universe's ability to surprise and challenge us. The idea that even black holes, the ultimate cosmic prisons, might not be as impenetrable as we once thought is both humbling and exhilarating. What other secrets do these enigmatic objects hold? The journey to uncover the answers continues, drawing us ever deeper into the mysteries of the cosmos. Now, turning to another fascinating enigma, we delve into the question, are there naked singularities? Unlike the black holes we've come to know, which are shrouded by their event horizons, naked singularities are hypothetical objects where the singularity, a point of infinite density, is exposed to the universe. This means they could, in theory, be observed directly, offering a rare glimpse into the extreme physics that govern these regions of spacetime. But here's the catch. Most physicists believe such objects shouldn't exist, thanks to a principle known as the cosmic censorship conjecture. Proposed by physicist Roger Penrose, the cosmic censorship conjecture suggests that singularities must always be hidden behind an event horizon. In other words, nature abhors a naked singularity. The idea is that the universe has a kind of built-in censorship mechanism, preventing the chaotic and unpredictable effects of a singularity from influencing the rest of the cosmos. This conjecture has been a cornerstone of black hole physics, providing a comforting framework that keeps the wildest aspects of singularities out of sight. However, not everyone is convinced. Some theorists argue that under specific conditions, such as during the collapse of certain types of stars or in the presence of exotic matter, naked singularities might form. These scenarios challenge the cosmic censorship conjecture and open the door to a universe where singularities could be visible. If such objects exist, they would revolutionize our understanding of gravity, spacetime, and the very fabric of reality. Imagine being able to observe a singularity directly, free from the veil of an event horizon. The implications for physics would be nothing short of groundbreaking. Yet the debate remains unresolved. While mathematical models suggest that naked singularities could form, no observational evidence has been found to support their existence. This leaves physicists in a tantalizing position, caught between the theoretical possibility of these objects and the lack of any concrete proof. The question of whether naked singularities are real or merely a quirk of our equations continues to spark intense discussion and research. As we explore this mystery, we're reminded of the delicate balance between theory and observation in science. The cosmic censorship conjecture offers a tidy explanation, but the universe has a way of defying our expectations. Could naked singularities be the exception to the rule, or are they simply a mathematical mirage? The search for answers pushes the boundaries of our knowledge, inviting us to question what we think we know about the cosmos. And as always, the universe holds its secrets close, challenging us to look deeper and think harder. Now, shifting our gaze to one of the most dazzling phenomena in the cosmos, we arrive at the question, what powers quasars? These celestial beacons, the brightest objects in the universe, shine with the intensity of trillions of stars, yet their brilliance is not fueled by starlight. Instead, quasars are powered by supermassive black holes, those colossal giants lurking at the hearts of galaxies. But how exactly do these black holes generate such staggering amounts of energy? At the core of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals toward the black hole, it forms a swirling disk of gas and dust known as an accretion disk. This disk heats up to unimaginable temperatures, glowing brightly as it converts gravitational energy into radiation. The result is a quasar, a cosmic lighthouse that can outshine entire galaxies. But here's the mystery. How do these black holes accumulate so much matter and energy in the first place? One theory suggests that supermassive black holes grow by devouring vast amounts of gas, dust, and even stars from their surroundings. Over billions of years, this steady diet allows them to reach their enormous sizes. Another possibility is that they form through the collision and merging of smaller black holes, a process that could accelerate their growth in the early universe. Yet, despite these ideas, the exact mechanisms remain unclear. Why do some supermassive black holes become voracious eaters, powering luminous quasars, while others remain quiet and dormant? The answer may lie in the environment surrounding the black hole. Active quasars are often found in galaxies with abundant gas and dust, providing ample fuel for the accretion disk. In contrast, dormant quasars might reside in galaxies where the gas supply has been depleted, leaving the black hole starved and inactive. But this raises another question: what triggers the transition between these states? Could a sudden influx of matter reignite a dormant quasar, or are there other factors at play? Adding to the intrigue, quasars are not just relics of the distant past. While many of the brightest quasars existed billions of years ago, during a period known as the Quasar epoch, some are still active today. This suggests that the conditions needed to power quasars can arise at different times in the universe's history. But what causes these conditions to change? Is it the result of galactic collisions, the movement of gas clouds, or something else entirely? As we ponder these questions, we're reminded of the intricate dance between black holes and their surroundings. Quasars are not just cosmic curiosities, they are windows into the processes that shape galaxies and the universe itself. By studying them, we gain insights into how supermassive black holes grow, how galaxies evolve, and how the universe's most extreme environments operate. Yet, for all we've learned, the full story of what powers quasars remains shrouded in mystery, inviting us to explore further and uncover the secrets of these luminous giants. Now, turning to the very heart of galactic mysteries, we find ourselves asking, how do supermassive black holes form? These colossal entities, often millions to billions of times more massive than our Sun, sit at the centers of galaxies, shaping their evolution and influencing their surroundings. Yet, their origins remain one of the most perplexing questions in astrophysics. How did these giants come to be, and how did they grow so massive so quickly in the early universe? One of the biggest challenges in understanding supermassive black holes is their sheer size. To reach such enormous masses, they would have needed to accumulate vast amounts of matter over time. But here's the puzzle. Some of the earliest quasars, powered by supermassive black holes, existed when the universe was less than 1 billion years old. How could these black holes have grown so large in such a short span of cosmic time? This rapid growth defies our current understanding of black hole formation and evolution. One leading theory suggests that supermassive black holes could have formed from the collapse of massive gas clouds in the early universe. These clouds, dense and turbulent, might have collapsed directly into black holes without ever forming stars. These direct collapse black holes could have started out with masses thousands of times greater than typical stellar black holes, giving them a head start in the race to grow even larger. Over time, they could have continued to accumulate matter, eventually reaching the staggering sizes we observe today. Another possibility is that supermassive black holes grew through the merging of smaller black holes. In the chaotic early universe, galaxies were closer together, and collisions between them were more frequent. These galactic mergers could have brought multiple black holes together, allowing them to combine and grow into the supermassive giants we see today. This process, known as hierarchical merging, might explain how black holes could grow rapidly in the dense environments of the early universe. Yet, even with these theories, there are still gaps in our understanding. For instance, how did the first seed black holes form? Were they the remnants of the first generation of stars, or did they arise from entirely different processes? And once these seeds existed, what conditions allowed them to grow so quickly? Some researchers propose that the intense radiation and turbulence of the early universe played a role, while others suggest that the presence of dark matter might have influenced their growth. Adding to the complexity, supermassive black holes are not uniform. Some are relatively quiet, while others, like those powering quasars, are incredibly active. This variation suggests that their formation and growth might depend on their environment. Galaxies with abundant gas and frequent collisions might foster the growth of supermassive black holes, while those in quieter regions might see slower, more gradual growth. As we explore these questions, we're reminded of the intricate interplay between black holes and their cosmic surroundings. Supermassive black holes are not just isolated objects. They are deeply connected to the galaxies they inhabit, influencing and being influenced by their environments. By studying their origins, we gain insights into the formation of galaxies, the evolution of the universe, and the fundamental processes that shape the cosmos. Yet, for all we've learned, the mystery of how supermassive black holes form remains unsolved. Each new discovery brings us closer to understanding these cosmic giants, but also raises new questions, inviting us to delve deeper into the mysteries of the universe. As we continue to explore, we may one day uncover the secrets of how these colossal black holes came to be, shedding light on one of the most profound enigmas in astrophysics. Now, shifting our gaze to one of the most dramatic events in the cosmos, we ask, what happens when two black holes collide? This cosmic spectacle, once purely theoretical, became a reality in 2015 when scientists detected gravitational waves for the first time. These ripples in spacetime, predicted by Einstein over a century ago, confirmed that black hole mergers are not just possible, they are happening across the universe. But what exactly unfolds during such a collision, and what mysteries remain about the aftermath? When two black holes spiral toward each other, they begin a dance that can last millions of years. As they draw closer, their immense gravitational pull distorts spacetime, sending out gravitational waves that ripple across the universe. These waves carry energy away from the system, causing the black holes to lose momentum and spiral even closer together. Eventually, they merge in a cataclysmic event, releasing an enormous burst of energy in the form of gravitational waves. This energy is so immense that, for a brief moment, the merger can outshine all the stars in the observable universe combined. But what happens after the collision? The resulting black hole is often more massive than either of its predecessors, but its properties are not simply the sum of the two. For instance, the new black hole spin is a mystery. While we can predict some aspects of its rotation based on the spins of the original black holes, the exact outcome depends on the complex dynamics of the merger. Scientists are still working to understand how the spins of the merging black holes influence the final product. Another intriguing question is what happens to the energy released during the collision. While most of it escapes as gravitational waves, some energy might be emitted in other forms, such as electromagnetic radiation. However, black holes are famously dark, and detecting any light or radiation from a merger is incredibly challenging. Some theories suggest that if the black holes are surrounded by gas or dust, the collision could heat this material, producing a faint glow. But so far, such emissions have not been definitively observed. The aftermath of a black hole merger also raises questions about the nature of spacetime itself. During the collision, the event horizons of the two black holes merge into one, creating a single, larger horizon. But what happens to the information about the original black holes? According to the no-hair theorem, the final black hole should be described only by its mass, charge, and spin. Yet, this raises questions about whether information is truly lost or somehow preserved in the gravitational waves or other remnants of the merger. One of the most fascinating aspects of black hole mergers is their role in shaping the universe. These events are not just isolated phenomena, they are part of the larger cosmic story. By studying them, we gain insights into the growth of supermassive black holes, the evolution of galaxies, and the nature of gravity itself. Each merger detected through gravitational waves provides a new piece of the puzzle, helping us understand how black holes form, grow, and interact. Yet, despite the progress we've made, many mysteries remain. For example, how common are black hole mergers in the universe? Are there different types of mergers depending on the sizes and spins of the black holes involved? And what can these collisions tell us about the fundamental laws of physics? As we continue to detect more mergers and refine our observations, we may uncover answers to these questions, shedding light on one of the most violent and enigmatic processes in the cosmos. As we ponder the mysteries of black hole collisions, we're reminded of the dynamic and ever-changing nature of the universe. These events, though fleeting, leave an indelible mark on the fabric of spacetime, offering us a glimpse into the profound forces that shape our cosmos. With each new discovery, we move closer to unraveling the secrets of these cosmic encounters, deepening our understanding of the universe and our place within it. Now, turning to a question that challenges our very understanding of black holes. Do black holes have hair? This might sound like an odd question, but in the world of astrophysics, it's a profound mystery. The no-hair theorem, a cornerstone of black hole physics, suggests that black holes are remarkably simple objects. According to this theorem, a black hole can be fully described by just three properties: its mass, its electric charge, and its spin. Everything else, every detail about the matter that fell into the black hole, is seemingly erased. This idea implies that black holes are, in a sense, bald, with no additional features or hair to distinguish them. But here's where things get interesting. While the no-hair theorem is elegant and widely accepted, it's not without its critics. Some scientists argue that black holes might, in fact, have hair, subtle, hidden features that could reveal more about their nature. These features could include remnants of the matter that formed the black hole or traces of the processes that shaped it. If black holes do have hair, it could mean that they're not as simple as we once thought, and that they might hold clues to the deeper workings of the universe. One area of debate centers on quantum mechanics. In the quantum realm, information is never truly lost, it's always preserved in some form. This principle seems to clash with the no-hair theorem, which suggests that black holes erase information about the matter they consume. If black holes do have hair, it could provide a way to reconcile these two ideas, offering a bridge between the worlds of quantum mechanics and general relativity. Another intriguing possibility is that black holes might have soft hair, a term coined by physicists to describe extremely subtle features that could exist on the event horizon. These features, if they exist, would be incredibly difficult to detect, but they could carry information about the black hole's history. For example, they might encode details about the objects that fell into the black hole or the forces that shaped its formation. Detecting such hair would require incredibly precise measurements far beyond our current capabilities, but the implications would be groundbreaking. The debate over whether black holes have hair isn't just an academic exercise. It has real consequences for our understanding of the universe. If black holes are as simple as the no-hair theorem suggests, they might be the ultimate cosmic erasers, wiping away all traces of the matter they consume. But if they have hair, they could be cosmic storytellers, preserving information about their past in ways we're only beginning to imagine. As we continue to explore this mystery, we're reminded of how much we still have to learn about black holes. Each new discovery, whether it supports the no-hair theorem or challenges it, brings us closer to understanding these enigmatic objects. And with every step forward, we uncover new questions, pushing the boundaries of our knowledge and deepening our appreciation for the complexity of the cosmos. Now, shifting our gaze to a question that seems almost paradoxical. Can black holes die? At first glance, black holes appear to be the ultimate cosmic predators, devouring everything that crosses their path. But what if these seemingly immortal giants could, in fact, fade away? This brings us to one of the most fascinating predictions in modern physics, Hawking radiation. Named after the legendary physicist Stephen Hawking, this theory suggests that black holes aren't entirely black. Instead, they emit a faint glow of particles, slowly losing energy over time. This process, known as Hawking radiation, occurs due to quantum effects near the event horizon. Pairs of particles and antiparticles constantly pop into existence in empty space, and when this happens near a black hole, one particle can fall in while the other escapes. The escaping particle carries away a tiny bit of the black hole's energy, causing it to shrink ever so slightly. Over unimaginably long timescales, this process could lead to the complete evaporation of a black hole. But here's where the mystery deepens. If a black hole evaporates, what happens to all the matter and information it once contained? According to the laws of quantum mechanics, information can never be truly destroyed. It must be preserved in some form. Yet, the no-hair theorem suggests that black holes erase all information about the matter they consume. This creates a paradox. If a black hole evaporates completely, where does the information go? Does it somehow escape with the Hawking radiation, or is it lost forever? This question remains one of the most hotly debated topics in theoretical physics. Another unresolved issue is the final moments of a black hole's life. As a black hole shrinks, its temperature increases and the rate of Hawking radiation accelerates. In its final moments, the black hole would release a burst of energy, but what exactly happens at the very end? Does it vanish in a flash of light, leaving nothing behind? Or does it leave behind some remnant, perhaps a tiny, stable object that preserves the information? These questions are still wide open, and answering them could revolutionize our understanding of black holes, quantum mechanics, and the nature of reality itself. The idea that black holes can die challenges our intuition and forces us to rethink the very nature of these cosmic giants. It's a reminder that even the most seemingly permanent structures in the universe are subject to change, governed by laws we're still striving to understand. As we continue to explore this mystery, we're not just uncovering the secrets of black holes, we're also probing the deepest questions about the fabric of space, time, and existence. Now, venturing into one of the most speculative and mind-bending mysteries of black holes, what lies beyond the singularity, at the heart of a black hole, where gravity becomes infinitely strong and spacetime curves to an extreme, lies the singularity, a point where the laws of physics as we know them cease to function. But what happens beyond this point? Is it truly the end, or could it be a gateway to something entirely unknown? One intriguing possibility is that singularities might connect to wormholes, hypothetical tunnels through spacetime that could link distant regions of the universe, or even different universes altogether. These cosmic shortcuts, often called Einstein-Rosen bridges, are predicted by the equations of general relativity. However, the existence of wormholes remains purely theoretical, as no observational evidence has been found to support them. Even if they do exist, traversing a wormhole would require exotic matter with negative energy to keep it stable, something we have yet to discover. Another fascinating idea is that singularities could lead to alternate universes or entirely new dimensions. Some theories suggest that the extreme conditions inside a black hole might create a bounce, where collapsing matter rebounds and gives birth to a new universe. This concept, while speculative, offers a tantalizing glimpse into the possibility that black holes are not just cosmic dead ends but creators of entirely new realities. However, testing this idea is incredibly challenging, as the singularity itself is hidden behind the event horizon, forever beyond our direct observation. The concept of extra dimensions, often explored in string theory, also plays a role in these speculations. If our universe has more than the three spatial dimensions we experience, singularities might serve as portals to these hidden realms. Yet, like wormholes and alternate universes, the existence of extra dimensions remains unproven, leaving these ideas firmly in the realm of theoretical physics. The challenge of exploring what lies beyond the singularity lies in the limitations of our current understanding. General relativity, which predicts singularities, breaks down at these extreme conditions, and quantum mechanics, which governs the behavior of particles at the smallest scales, has yet to be successfully unified with gravity. Without a complete theory of quantum gravity, we can only speculate about the true nature of what lies beyond. As we ponder these possibilities, we're reminded of the profound mysteries that black holes continue to hold. The singularity represents not just a boundary of our knowledge, but also a frontier of discovery, where the answers could reshape our understanding of the universe itself. While the journey to uncover these secrets is fraught with challenges, it's also filled with the promise of unlocking some of the most profound truths about existence. Now, shifting our gaze to another captivating mystery, could black holes serve as portals to other universes? This idea, while sounding like science fiction, has roots in the equations of general relativity. At the heart of this concept lies the Einstein-Rosen bridge, more commonly known as a wormhole, a theoretical tunnel through spacetime that could connect distant regions of the universe or even entirely different universes. The mathematics suggests that such bridges could form within black holes, where the extreme curvature of spacetime might create a passage to another realm. But here's the catch: these wormholes, if they exist, would be incredibly unstable. Without exotic matter, a hypothetical substance with negative energy, to hold them open, they would collapse almost instantly, making them impossible to traverse. The idea of black holes as gateways to other universes is further fueled by theories in quantum mechanics and string theory. Some models propose that the singularity at the center of a black hole might not be a dead end but a bridge to another universe or a different region of spacetime. In this scenario, the matter and energy swallowed by a black hole could emerge in another universe, effectively making black holes cosmic recycling centers. However, this remains purely speculative, as no observational evidence supports the existence of such connections. The event horizon, the point of no return, shrouds the interior of a black hole in mystery, making it impossible for us to peer inside and verify these theories. Adding to the intrigue is the concept of the multiverse, the idea that our universe is just one of many. If black holes do act as portals, they could be the cosmic highways linking these parallel realities. Yet, the multiverse itself is a highly debated topic with no direct evidence to confirm its existence. Without a way to observe or test these ideas, they remain tantalizing possibilities rather than established facts. The challenge in exploring this mystery lies in the limitations of our current scientific tools. General relativity provides the framework for understanding black holes and wormholes, but it breaks down at the singularity where quantum effects dominate. Until we develop a unified theory of quantum gravity, which reconciles general relativity with quantum mechanics, the true nature of black holes and their potential as portals will remain one of the universe's greatest enigmas. As we ponder the possibility of black holes as gateways to other universes, we're reminded of how much we still have to learn about the cosmos. These cosmic giants, once thought to be mere destroyers of light and matter, might hold the keys to understanding the very fabric of reality. While the answers remain elusive, the journey to uncover them continues to inspire awe and curiosity, pushing the boundaries of human knowledge ever further. Now, turning to another cosmic enigma, let's explore the phenomenon of gamma-ray bursts, some of the most powerful explosions in the universe. These bursts, which can outshine entire galaxies for a brief moment, are often linked to black holes, adding another layer of mystery to these already fascinating objects. But what exactly causes these colossal bursts of energy, and how do black holes play a role in their creation? Gamma-ray bursts are typically divided into two categories: long-duration bursts, which last more than 2 seconds, and short-duration bursts, which are over in a flash. Long bursts are thought to occur when massive stars collapse at the end of their lives, forming black holes in the process. As the star's core implodes, it triggers a supernova explosion, and the newly formed black hole launches jets of particles at nearly the speed of light. These jets, packed with energy, produce the intense gamma-ray emission we observe. Short bursts, on the other hand, are believed to result from the collision of two neutron stars or a neutron star merging with a black hole. The immense gravitational forces at play during these events release a torrent of energy, manifesting as a gamma-ray burst, but here's where the mystery deepens. While we have a general understanding of the conditions that lead to gamma-ray bursts, the exact mechanisms behind their production remain unclear. For instance, how do black holes generate such focused and energetic jets? What processes within the black hole's environment accelerate particles to such extreme speeds? And why do some black holes produce these bursts while others do not? These questions highlight the complexity of the extreme physics at work near black holes, where gravity, magnetic fields, and particle interactions create conditions unlike anything we can replicate on Earth. Adding to the intrigue is the fact that gamma-ray bursts are not just spectacular cosmic fireworks, they also serve as probes of the early universe. Because these bursts are so bright, they can be detected from billions of light years away, offering a glimpse into the distant past. By studying their properties, scientists hope to learn more about the formation of black holes, the evolution of galaxies, and even the expansion rate of the universe. Yet, despite their importance, gamma-ray bursts remain one of the most elusive phenomena in astrophysics, with many unanswered questions about their origins and behavior. As we continue to unravel the mysteries of gamma-ray bursts and their connection to black holes, we're reminded of the sheer power and unpredictability of the cosmos. These bursts, born in the most extreme environments imaginable, challenge our understanding of physics and push the limits of our observational capabilities. While the answers remain hidden for now, each new discovery brings us closer to understanding the forces that shape the universe and the role black holes play in these extraordinary events. Now, shifting our gaze to another profound question, let's ponder whether black holes have a size limit. Can these cosmic giants grow endlessly, or is there a cap to how massive they can become? This mystery takes us to the very edges of our understanding of the universe, where the laws of physics and the nature of spacetime itself come into play. At first glance, it might seem like black holes could grow indefinitely, consuming everything in their path. After all, their gravitational pull is so strong that not even light can escape once it crosses the event horizon. However, the reality is far more nuanced. The growth of a black hole is constrained by several factors, including the availability of matter and the expansion of the universe. In regions where matter is sparse, black holes may struggle to grow as there simply isn't enough material to feed them. Even in dense environments like the centers of galaxies, black holes can only consume so much before they reach a point of diminishing returns. One key factor limiting black hole growth is the Eddington limit, a theoretical boundary that defines the maximum rate at which a black hole can accrete matter. Beyond this limit, the radiation emitted by the infalling material becomes so intense that it pushes back against the incoming matter, effectively putting a brake on further growth. This balance between gravity and radiation ensures that black holes don't grow uncontrollably, even in the most matter-rich environments. But what about supermassive black holes, which can weigh billions of times the mass of our Sun? How did they become so enormous? The answer lies in the early universe, where conditions were vastly different. In the dense, chaotic environment of the young cosmos, black holes could grow rapidly by merging with one another and consuming vast amounts of gas and dust. Over billions of years, these mergers and accretion events allowed supermassive black holes to reach their staggering sizes. Yet, even these giants may have a limit. Some theories suggest that the expansion of the universe could eventually isolate black holes, cutting them off from new sources of matter and halting their growth. Another intriguing possibility is that black holes might reach a point where their own gravity becomes too weak to sustain further growth. As a black hole grows larger, its event horizon, the point of no return expands, but the gravitational pull at the horizon weakens relative to its size. This means that, beyond a certain point, a black hole might not be able to pull in matter as efficiently, effectively capping its growth. The question of whether black holes have a size limit also ties into the broader mysteries of the universe's structure and evolution. If black holes can grow indefinitely, what does that mean for the fate of galaxies and the cosmos as a whole? Could there be black holes so massive that they dominate entire regions of space, reshaping the fabric of the universe? Or are there natural limits that prevent such scenarios? These questions remain unanswered, but they highlight the profound interplay between black holes and the universe itself. As we continue to explore the mysteries of black holes, the question of their size limit reminds us of the delicate balance that governs the cosmos. Whether through the availability of matter, the expansion of the universe, or the fundamental laws of physics, black holes are bound by forces that shape their growth and evolution. While the answers remain elusive, each discovery brings us closer to understanding the true nature of these enigmatic objects and their place in the grand tapestry of the universe. Now, turning to the fate of matter as it plunges into a black hole, we enter a realm where the laws of physics as we know them begin to unravel. Imagine a star, a planet, or even a cloud of gas drifting too close to a black hole's immense gravitational pull. As it approaches the event horizon, the point of no return, the matter begins a dramatic and violent transformation. But what exactly happens to it? This is one of the most fascinating and unresolved mysteries in astrophysics. As matter nears the event horizon, it experiences extreme tidal forces. These forces are so powerful that they stretch and compress the matter in a process known as spaghettification. Picture a piece of spaghetti being pulled apart. This is what happens to objects as they approach a black hole. The side of the object closer to the black hole feels a stronger gravitational pull than the side farther away, causing it to stretch into long, thin strands. This process tears apart stars, planets, and even atoms, reducing them to their most basic components. But the journey doesn't end there. Once the matter crosses the event horizon, it is lost to the outside universe forever. Inside, the laws of physics as we understand them break down. General relativity predicts that the matter is crushed into an infinitely dense point at the singularity, the very core of the black hole. However, this idea clashes with quantum mechanics, which suggests that information about the matter cannot simply disappear. This contradiction lies at the heart of the unresolved questions about the fate of matter in a black hole. One of the biggest mysteries is how matter is incorporated into the black hole's structure. Does it truly vanish into the singularity, or is there some other process at work? Some theories propose that the matter might be stored on the black hole's event horizon, encoded in the form of quantum information. This idea, known as the holographic principle, suggests that all the information about the matter could be preserved on the surface of the black hole like a cosmic hard drive. However, this remains speculative, and no one knows for sure how or where the information is stored. Another unresolved question is what happens to the matter's energy. As matter falls into a black hole, it releases enormous amounts of energy in the form of radiation, particularly in the case of supermassive black holes. This energy powers some of the brightest objects in the universe, such as quasars and active galactic nuclei. But how exactly is this energy generated, and what role does the matter play in the process? Scientists are still working to understand the intricate mechanisms at play. The fate of matter falling into a black hole also raises questions about the nature of spacetime itself. Does the matter truly reach the singularity, or does it encounter some other phenomenon that we have yet to discover? Could there be structures or layers within the black hole that we don't yet understand? These questions challenge our understanding of the universe and push the boundaries of both general relativity and quantum mechanics. As we continue to explore these mysteries, the fate of matter in black holes remains one of the most captivating and perplexing topics in modern science. It reminds us that even in the darkest corners of the universe, there are still secrets waiting to be uncovered. And with each discovery, we come closer to unraveling the true nature of these enigmatic cosmic giants. Now, shifting our gaze to the earliest moments of the universe, we encounter a fascinating possibility: primordial black holes. Unlike the black holes we're familiar with, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the chaotic aftermath of the Big Bang. These ancient black holes could be relics of a time when the universe was incredibly dense and hot, with fluctuations in density creating pockets of matter so compact that they collapse directly into black holes. But do they really exist? This question has puzzled scientists for decades and remains one of the most intriguing unsolved mysteries in cosmology. The idea of primordial black holes opens up a tantalizing window into the early universe. If they exist, they could range in size from tiny, subatomic specks to massive objects many times the mass of our Sun. Some theories even suggest that these black holes could account for a portion of the elusive dark matter that makes up most of the universe's mass. Dark matter, which doesn't emit light or interact with electromagnetic forces, has been detected only through its gravitational effects. Primordial black holes, if they're out there, could be a key piece of this cosmic puzzle. But how do we detect something so mysterious? Primordial black holes, especially the smaller ones, would be incredibly difficult to observe directly. However, scientists have proposed several indirect methods to search for them. One approach involves looking for the gravitational effects they might have on light from distant stars, a phenomenon known as microlensing. If a primordial black hole passes between Earth and a star, its gravity could bend and magnify the star's light, creating a temporary brightening that could be detected by telescopes. Another method involves searching for the bursts of radiation that could be emitted if a primordial black hole evaporates through Hawking radiation. a process that becomes more significant for smaller black holes. The potential existence of primordial black holes also raises questions about their role in shaping the universe. Could they have influenced the formation of galaxies or the distribution of dark matter? Some theories even suggest that these ancient black holes might have served as seeds for the supermassive black holes we see at the centers of galaxies today. If true, this would mean that primordial black holes played a crucial role in the cosmic evolution of the universe. Yet, despite decades of searching, no definitive evidence of primordial black holes has been found. This absence leaves scientists grappling with the question of whether they truly exist or if they're simply a theoretical curiosity. The search continues, driven by the hope that these enigmatic objects could unlock new insights into the early universe, dark matter, and the fundamental nature of black holes themselves. As we explore this mystery, we're reminded of how much we still have to learn about the cosmos. Primordial black holes, if they exist, could be a hidden thread connecting the earliest moments of the universe to the structures we see today. Their discovery would not only solve a long-standing mystery, but also deepen our understanding of the universe's origins and evolution. And so, the hunt for these ancient cosmic relics continues, a testament to the enduring curiosity and ingenuity of humanity in the face of the unknown. Now, venturing into one of the most mind-bending ideas in modern cosmology, we arrive at the question: could black holes be the birthplaces of entirely new universes? This speculative theory suggests that within the depths of a black hole, beyond the singularity where our understanding of physics breaks down, a new universe might be born. Imagine a black hole not as a cosmic dead end, but as a gateway to an entirely new reality, a place where the laws of physics as we know them are rewritten and a new cosmos begins to unfold. The idea hinges on a concept known as the black hole bounce. According to this theory, when matter is crushed to infinite density at the singularity, it doesn't simply vanish. Instead, it rebounds, creating a new spacetime that expands outward, much like the Big Bang that gave rise to our own universe. In this scenario, every black hole could be a seed for a new universe, hidden within its own event horizon. This would mean that our universe itself might have originated from a black hole in another, pre-existing cosmos, creating a vast, interconnected multiverse. But how could we ever test such a radical idea? The challenge lies in the fact that the singularity is shrouded by the event horizon, a boundary beyond which no information can escape. This makes it impossible for us to observe what happens inside a black hole directly. However, some physicists have proposed that subtle clues might be found in the properties of our own universe. For example, if our universe was born from a black hole bounce, it might carry imprints of its parent universe in the form of irregularities in the cosmic microwave background radiation or the distribution of galaxies. These faint echoes could, in theory, provide evidence for the existence of other universes. Another intriguing aspect of this theory is its implications for the nature of time and causality. If black holes can create new universes, then time might not flow in a single, linear direction as we experience it. Instead, it could branch off into multiple timelines, each corresponding to a new universe born from a black hole. This would fundamentally alter our understanding of cause and effect, suggesting that the universe is far more interconnected and dynamic than we ever imagined. Yet, despite its fascinating possibilities, the idea of black holes creating new universes remains highly speculative. It pushes the boundaries of our current understanding of physics, requiring a unified theory that combines general relativity with quantum mechanics, a goal that has eluded scientists for decades. Without such a theory, the concept of black hole bounces remains in the realm of theoretical exploration, a tantalizing possibility that challenges our deepest assumptions about the nature of reality. As we ponder this extraordinary idea, we're reminded of how much we still have to learn about the cosmos. The notion that black holes could be cosmic creators, birthing new universes within their depths, invites us to rethink our place in the grand tapestry of existence. It's a reminder that the universe is full of mysteries waiting to be uncovered, and that every answer we find may lead to even more profound questions. And so, the search for understanding continues, driven by the boundless curiosity that defines our species. Now shifting our gaze to the cosmic dance between black holes and galaxies, we find ourselves asking, what role do these enigmatic objects play in the birth and evolution of galaxies? Supermassive black holes, often found at the heart of galaxies, seem to be more than just passive residents. They appear to be deeply intertwined with the very fabric of their galactic homes, influencing their growth, structure, and even their ultimate fate. At the center of nearly every large galaxy lies a supermassive black hole, millions or even billions of times more massive than our Sun. These colossal objects are not mere bystanders, they are active participants in the life of their galaxies. One of the most intriguing questions is whether supermassive black holes are the architects of galaxy formation or simply a byproduct of it. Do they shape galaxies from the beginning, or do they grow in tandem with the stars and gas around them? One compelling theory suggests that supermassive black holes play a crucial role in regulating star formation. As matter falls into a black hole, it releases enormous amounts of energy in the form of radiation and powerful jets. These outflows can heat up surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, black holes act as cosmic regulators, controlling the pace at which galaxies evolve. Without this balancing act, galaxies might burn through their gas too quickly, leading to a very different universe than the one we see today. But the relationship between black holes and galaxies is far from one-sided. Galaxies also influence their central black holes, feeding them with gas and stars. When galaxies collide, their supermassive black holes can merge, releasing gravitational waves that ripple through spacetime. These mergers can trigger bursts of star formation and reshape the structure of the newly combined galaxy. It's a dynamic interplay where black holes and galaxies grow and evolve together, each shaping the other in profound ways. Yet, many questions remain unanswered. For instance, how do supermassive black holes grow so massive so quickly in the early universe? Some of these black holes appear to have reached their enormous sizes just a few 100 million years after the Big Bang, a timescale that challenges our understanding of how they could accumulate so much matter. Are there mechanisms at play that we have yet to discover, or do these black holes form in ways that defy our current models? Another mystery lies in the diversity of galaxies and their black holes. Not all galaxies with supermassive black holes are active, and not all active galaxies have the same level of activity. What determines whether a black hole becomes a quasar, emitting intense radiation, or remains quiet and dormant? The answers to these questions could reveal deeper truths about the relationship between black holes and their galactic environments. As we explore these mysteries, we're reminded of the intricate connections that bind the cosmos together. Black holes are not isolated anomalies. They are integral to the story of galaxies, shaping and being shaped by the vast structures they inhabit. Understanding their role in galaxy formation is not just about solving a cosmic puzzle, it's about uncovering the fundamental processes that govern the universe itself. And as we continue to probe these questions, we move closer to unraveling the grand tapestry of existence, one thread at a time. Now turning to the fascinating intersection of black holes and the laws of thermodynamics, we find ourselves grappling with a profound question. Do these cosmic giants defy the very principles that govern energy, heat, and entropy? At first glance, black holes seem to challenge our understanding of thermodynamics. But as we dig deeper, we uncover a complex and intriguing relationship that raises more questions than answers. One of the key concepts here is black hole entropy, a measure of the disorder or randomness within a black hole. In the 1970s, physicist Jacob Bekenstein proposed that black holes possess entropy, a groundbreaking idea that linked these mysterious objects to the second law of thermodynamics. This law states that the total entropy of a closed system can never decrease over time. But how does this apply to black holes, which are often thought of as regions where information and matter seemingly disappear? Stephen Hawking further expanded on this idea by introducing the concept of Hawking radiation, which suggests that black holes can emit particles and lose mass over time. This process implies that black holes have a temperature, another thermodynamic property. If black holes have both entropy and temperature, they must somehow fit into the framework of thermodynamics. But here's the twist: when matter falls into a black hole, it appears to vanish from the universe, seemingly reducing the total entropy. This creates a paradox, as it seems to violate the second law of thermodynamics. To resolve this, physicists have proposed that the entropy of a black hole is encoded on its event horizon, the boundary beyond which nothing can escape. This idea, known as the holographic principle, suggests that all the information about the matter that falls into a black hole is stored on its surface like a cosmic hard drive. If true, this would mean that black holes don't actually destroy entropy, but instead redistribute it in a way we don't yet fully understand. Yet, the mystery deepens when we consider the fate of information in a black hole. According to quantum mechanics, information cannot be destroyed, but black holes seem to contradict this principle. This conflict, known as the information paradox, remains one of the most significant unsolved problems in physics. How can black holes reconcile the laws of thermodynamics with the principles of quantum mechanics? Is there a deeper connection between these two frameworks that we're missing? Another unresolved question is whether black holes can reach a state of equilibrium with their surroundings. In thermodynamics, systems tend to move toward equilibrium, where energy is evenly distributed. But black holes, with their immense gravitational pull, seem to disrupt this balance. Can a black hole ever truly be in thermodynamic equilibrium, or does its very nature prevent it from conforming to this principle? As we explore these questions, we're reminded that black holes are not just cosmic curiosities, they are laboratories for testing the limits of our understanding. The relationship between black holes and thermodynamics challenges us to rethink fundamental concepts like entropy, information, and energy. It's a reminder that the universe is far more complex and interconnected than we often assume, and that even the most established laws of physics may have exceptions waiting to be discovered. With these mysteries still unresolved, we're left to wonder: will black holes ultimately force us to rewrite the laws of thermodynamics, or will they reveal a deeper harmony between these laws and the fabric of the cosmos? As we continue to probe these questions, we move closer to uncovering the true nature of these enigmatic objects and their place in the grand tapestry of the universe. Now shifting our focus to one of the most intriguing predictions in modern physics, we delve into the nature of Hawking radiation. This phenomenon, first proposed by Stephen Hawking in the 1970s, suggests that black holes are not entirely black after all. Instead, they emit particles over time, slowly losing mass and energy in a process that challenges our understanding of these cosmic giants. Hawking radiation arises from quantum effects near the event horizon of a black hole. According to quantum mechanics, pairs of particles and antiparticles constantly pop into existence and annihilate each other in empty space. Near the event horizon, however, one of these particles can fall into the black hole while the other escapes into space. The escaping particle carries away energy, effectively causing the black hole to lose mass. Over time, this process could lead to the complete evaporation of a black hole, a concept that seems almost paradoxical given their reputation as insatiable cosmic vacuums. But the exact mechanism behind Hawking radiation remains shrouded in mystery. For instance, what determines the spectrum of this radiation? Is it uniform, or does it vary depending on the size and properties of the black hole? These questions are crucial because they could reveal deeper insights into the quantum nature of spacetime itself. Additionally, the process raises unresolved questions about the information paradox. If a black hole evaporates completely, what happens to all the information about the matter that fell into it? Does it disappear forever, or is it somehow encoded in the radiation? Another puzzling aspect is the temperature of Hawking radiation. Smaller black holes are predicted to emit radiation at higher temperatures, while larger ones emit it at much lower temperatures. This inverse relationship between size and temperature is counterintuitive and raises questions about how black holes interact with their surroundings. Could we ever detect Hawking radiation from supermassive black holes, or is it only observable in smaller, hypothetical black holes? The implications of Hawking radiation extend far beyond black hole evaporation. If confirmed, it would provide a rare bridge between quantum mechanics and general relativity, two frameworks that have so far resisted unification. It could also offer clues about the ultimate fate of black holes and the universe itself. For example, if black holes can evaporate completely, what remains in their place? A burst of energy, a remnant of spacetime, or perhaps nothing at all? As we explore these questions, we're reminded that Hawking radiation is more than just a theoretical curiosity. It's a window into the deepest mysteries of the cosmos. It challenges us to rethink our understanding of black holes, quantum mechanics, and the very fabric of reality. And while many questions remain unanswered, the pursuit of these answers continues to push the boundaries of human knowledge, bringing us closer to unraveling the true nature of the universe. Now turning to one of the most mind-bending possibilities in the realm of black holes, we explore the tantalizing question: could black holes be used for time travel? This idea, while firmly rooted in the realm of speculation, has captured the imagination of scientists and science fiction enthusiasts alike. At its core, the concept hinges on the extreme warping of spacetime caused by black holes, which could, in theory, create pathways for time travel. The theoretical basis for this idea lies in something called closed time-like curves. These are hypothetical paths through spacetime that loop back on themselves, allowing an object or person to return to their own past. In the context of black holes, such curves could form under specific conditions, particularly around rotating black holes, also known as Kerr black holes. The intense gravitational field of a Kerr black hole could twist spacetime so severely that it creates a loop, effectively bending time into a circle. If such a loop exists, it might be possible to travel along it and emerge at an earlier point in time. However, the practical challenges of testing this idea are immense. For one, closed time-like curves are purely theoretical constructs, and no observational evidence supports their existence. Even if they do exist, navigating them would require technology far beyond our current capabilities. The extreme conditions near a black hole, including tidal forces that would tear apart any known material, make the idea of approaching one, let alone using it for time travel, seem almost impossible. Another major hurdle is the potential for paradoxes. If time travel were possible, it could lead to scenarios like the famous grandfather paradox, where a time traveler might prevent their own existence. Such paradoxes challenge our understanding of cause and effect, raising questions about whether the laws of physics would even allow closed time-like curves to exist in the first place. Despite these challenges, the idea of black holes as time travel portals continues to inspire research and debate. Some theories suggest that quantum mechanics might offer a way to resolve the paradoxes, while others propose that the universe might naturally prevent such loops from forming. For now, the concept remains a fascinating thought experiment, pushing the boundaries of our understanding of space-time and the fundamental laws of physics. As we ponder the possibilities, we're reminded that black holes are not just cosmic vacuum cleaners. They're laboratories for exploring the most extreme and mysterious aspects of the universe. Whether or not they can be used for time travel, they continue to challenge our imagination and drive us to uncover the secrets of the cosmos. And with that, we move closer to the next mystery, where the boundaries of reality are stretched even further. Now shifting our gaze to another cosmic spectacle, we delve into the enigmatic origins of supermassive black hole jets. These jets are among the most powerful and awe-inspiring phenomena in the universe, shooting out streams of particles at nearly the speed of light. But what exactly causes these jets, and why do only certain supermassive black holes produce them? These questions remain some of the most perplexing mysteries in astrophysics. Supermassive black holes, often found at the centers of galaxies, are surrounded by swirling disks of gas and dust known as accretion disks. As material from these disks spirals inward, it heats up and emits tremendous amounts of energy. In some cases, this process gives rise to relativistic jets, narrow beams of charged particles that blast outward from the black hole's poles. These jets can extend for thousands or even millions of light years, far beyond the boundaries of their host galaxies. The exact mechanism behind the formation of these jets is still unclear. One leading theory suggests that the intense magnetic fields generated by the spinning black hole and its accretion disk play a crucial role. These fields can twist and channel some of the infalling material into narrow, high-speed jets. Another idea proposes that the black hole's spin itself acts as a kind of cosmic engine, transferring energy to the jets. However, neither theory fully explains why only a fraction of supermassive black holes produce jets, while others remain relatively quiet. Adding to the mystery is the incredible efficiency of these jets. They can convert a significant portion of the infalling material's energy into kinetic energy, propelling particles to relativistic speeds. Yet, the precise processes that allow this energy transfer remain poorly understood. Scientists are also puzzled by the variability of these jets. Some appear to flare up and dim over time, while others remain steady for millions of years. Another unresolved question is the role of the environment surrounding the black hole. Some researchers believe that the presence of a dense, magnetized medium near the black hole might be necessary for jet formation. Others suggest that the orientation of the black hole's spin relative to its accretion disk could determine whether jets are produced. Despite decades of observation and theoretical work, no single explanation has emerged as definitive. The study of supermassive black hole jets is not just an academic pursuit, it has profound implications for our understanding of galaxy evolution. These jets can heat and reshape the gas in their host galaxies, influencing star formation and the growth of the black holes themselves. They may even play a role in regulating the growth of entire galaxy clusters. As we continue to explore this cosmic puzzle, we're reminded of the intricate and interconnected nature of the universe. The origin of supermassive black hole jets is a testament to the complexity of these cosmic giants and the many secrets they still hold. And with that, we prepare to uncover yet another layer of mystery, where the boundaries of our knowledge are pushed even further. Now shifting our focus to another cosmic enigma, we explore the intriguing possibility of a connection between black holes and dark energy. Dark energy, the mysterious force driving the accelerated expansion of the universe, remains one of the greatest puzzles in modern cosmology. But could black holes, those gravitational powerhouses, have a role to play in this cosmic dance? This question opens up a fascinating and unresolved mystery that challenges our understanding of both black holes and the universe itself. At first glance, black holes and dark energy seem like entirely separate phenomena. Black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. Dark energy, on the other hand, is a form of energy that permeates all of space and causes the universe to expand at an ever-increasing rate. Yet, some scientists have begun to speculate that these two cosmic entities might be more intertwined than we once thought. One of the key questions is whether black holes could contribute to dark energy. Some theories suggest that the immense gravitational fields of black holes might interact with the fabric of spacetime in ways that influence the expansion of the universe. For instance, the energy contained within black holes, particularly supermassive ones, could potentially have an effect on the overall energy density of the universe, which in turn affects the rate of expansion. However, this idea is still highly speculative, and no concrete evidence has been found to support it. Another angle of this mystery is whether dark energy influences black holes. Could the presence of dark energy alter the behavior or properties of black holes? Some researchers have proposed that dark energy might affect the growth rate of black holes or even their internal structure. For example, if dark energy exerts a kind of pressure on spacetime, it might subtly change how black holes accrete matter or emit radiation. Yet, these ideas remain theoretical, and the mechanisms by which such interactions could occur are far from understood. Adding to the complexity is the fact that dark energy itself is poorly understood. We know it exists because of its observable effects on the universe's expansion, but its true nature remains elusive. Is it a property of spacetime itself, or is it some form of exotic energy field? Without a clearer understanding of dark energy, it's difficult to determine how it might interact with black holes, if at all. The potential connection between black holes and dark energy also raises questions about the large-scale structure of the universe. If black holes do contribute to dark energy, they might play a role in shaping the cosmic web, the vast network of galaxies and galaxy clusters that make up the universe. Conversely, if dark energy influences black holes, it could affect how galaxies form and evolve over time. These possibilities highlight the intricate interplay between the smallest and largest scales in the cosmos. As we continue to probe this mystery, we're reminded of how much we still have to learn about the universe. The potential link between black holes and dark energy is a tantalizing clue that could help us unravel some of the deepest secrets of existence. And with that, we prepare to venture into yet another layer of cosmic mystery, where the boundaries of our understanding are pushed even further. Now turning to a question that challenges our understanding of scale in the cosmos, we delve into the mystery of the smallest possible black hole. While black holes are often imagined as colossal, universe-shaping giants, could there exist black holes so tiny they defy our expectations? This intriguing possibility opens up a realm of theoretical physics that pushes the boundaries of what we know about these enigmatic objects. At the heart of this mystery lies the concept of micro-black holes. Unlike the supermassive black holes that dominate the centers of galaxies or even the stellar mass black holes formed from collapsing stars, micro-black holes are hypothesized to be incredibly small, perhaps no larger than an atom. But how could such tiny black holes exist? One theory suggests they might have formed in the extreme conditions of the early universe, moments after the Big Bang, when the density of matter and energy was unimaginably high. In this chaotic environment, fluctuations in density could have created pockets of spacetime dense enough to collapse into black holes on a microscopic scale. Yet, the existence of micro-black holes remains purely theoretical. One of the biggest challenges is detecting them. If they do exist, their small size would make them incredibly difficult to observe directly. Some scientists have proposed that these tiny black holes might emit detectable radiation, such as Hawking radiation, as they slowly evaporate. However, the faint signals they would produce are far beyond our current observational capabilities. This raises the question, if micro-black holes are out there, how could we ever find them? Another unresolved question is whether micro-black holes could form naturally in the present-day universe. Under normal conditions, the collapse of matter into a black hole requires an immense amount of mass and gravitational force, which is why stellar mass black holes form from the depths of massive stars. But for a micro-black hole to form, the conditions would need to be extraordinary, perhaps involving exotic particles or extreme energies, such as those found in particle accelerators. Some theories even suggest that high-energy cosmic rays colliding with Earth's atmosphere could, in rare instances, create micro-black holes. However, no such events have ever been observed. The study of micro-black holes also intersects with the search for a unified theory of physics. In particular, theories like string theory and quantum gravity propose that spacetime might have additional dimensions beyond the four we experience. In these higher dimensional models, the formation of micro-black holes could occur at much lower energies than predicted by classical physics. This opens up the tantalizing possibility that experiments in particle physics might one day produce evidence of these elusive objects, offering a glimpse into the fundamental nature of reality. As we ponder the smallest possible black holes, we're reminded of the vast range of scales in the universe, from the microscopic to the cosmic. Whether or not micro-black holes exist, their study challenges us to rethink our assumptions about gravity, space-time, and the very fabric of the universe. And with that, we prepare to explore yet another layer of cosmic mystery, where the smallest questions often lead to the biggest revelations. Now shifting our focus to another fascinating enigma, we explore the question of whether black holes can have magnetic fields. At first glance, this might seem counterintuitive. After all, black holes are often thought of as regions where gravity is so intense that not even light can escape. So how could something as complex as a magnetic field exist in such a place? The answer lies in the intricate interplay between matter, energy, and the extreme conditions surrounding black holes. To understand this mystery, let's start with what we know about magnetic fields in space. Magnetic fields are typically generated by moving electric charges, such as those found in the swirling plasma around stars or in the accretion disks that surround black holes. These disks, made up of gas, dust, and other matter, spiral inward at incredible speeds, creating powerful electric currents. These currents, in turn, can produce magnetic fields. But here's the catch. Once matter crosses the event horizon of a black hole, it's lost to the outside universe. So, if the material generating the magnetic field disappears into the black hole, how can the field persist? This is where things get interesting. While the black hole itself may not have a magnetic field in the traditional sense, the environment around it can. The intense gravitational pull of a black hole can twist and amplify magnetic fields in its vicinity, creating structures known as magnetospheres. These magnetospheres can extend far beyond the event horizon, influencing the behavior of matter and energy in the surrounding space. For example, they can channel particles into powerful jets that shoot out from the poles of the black hole at nearly the speed of light. These jets are some of the most energetic phenomena in the universe, and their existence suggests that magnetic fields play a crucial role in shaping the behavior of black holes. But the mystery deepens when we consider the black hole's interior. According to general relativity, the singularity at the center of a black hole is a point of infinite density where the laws of physics as we know them break down. This raises the question, could a magnetic field survive in such an extreme environment? Some theories suggest that the intense gravitational forces might distort or even destroy magnetic fields within the black hole. Others propose that quantum effects could preserve certain aspects of these fields, offering a glimpse into the hidden physics at play. The implications of this mystery are profound. If black holes can indeed possess or influence magnetic fields, it could reshape our understanding of how they interact with their surroundings. Magnetic fields could play a key role in processes like accretion, jet formation, and even the emission of Hawking radiation. Moreover, studying these fields could provide clues about the nature of the singularity itself, potentially bridging the gap between general relativity and quantum mechanics. As we ponder the possibility of magnetic fields in black holes, we're reminded once again of the complexity and beauty of these cosmic phenomena. Whether or not black holes truly have magnetic fields, their influence on the universe is undeniable. And with that, we prepare to uncover yet another layer of mystery, where the forces of nature reveal themselves in ways that continue to challenge and inspire us. Now turning to one of the most mind-bending mysteries of black holes, we delve into the question of what happens to time near these cosmic giants. Time, as we experience it, is a constant, a steady flow that governs our lives. But near a black hole, this familiar concept is turned on its head. The immense gravitational pull of a black hole warps not just space, but time itself, creating effects that challenge our understanding of reality. Let's start with the phenomenon of time dilation. According to Einstein's theory of general relativity, gravity affects the passage of time. The stronger the gravitational field, the slower time moves relative to areas with weaker gravity. Near a black hole's event horizon, where gravity is at its most extreme, this effect becomes dramatic. For an observer far away from the black hole, time near the event horizon appears to slow down almost to a standstill. Imagine watching a clock falling toward the black hole. It would tick slower and slower until, from your perspective, it seems to freeze just before crossing the event horizon. But for someone falling into the black hole, time would feel normal. This stark difference in how time is experienced is one of the most striking consequences of black hole physics. But what happens to time inside the black hole? This is where the mystery deepens. Once past the event horizon, the pull of gravity becomes so overwhelming that all paths lead to the singularity at the center. Time, as we know it, ceases to behave in a linear fashion. Some theories suggest that time and space essentially swap roles inside a black hole. What we perceive as the inevitable march of time becomes a spatial dimension, while space itself becomes a one-way journey toward the singularity. This bizarre reversal raises profound questions about the nature of time and whether it can truly be said to exist in the conventional sense within a black hole. The implications of these effects are staggering. For one, they challenge our understanding of causality, the idea that cause must precede effect. Near a black hole, the extreme warping of time could create scenarios where the usual rules of cause and effect break down. This has led to speculation about whether black holes could serve as gateways to other regions of spacetime or even other universes, though such ideas remain firmly in the realm of theory. Another unresolved question is how time behaves at the singularity itself. At this point of infinite density, the laws of physics as we know them cease to function. Time, along with space, becomes meaningless. Some physicists propose that quantum effects might prevent the singularity from forming, replacing it with something entirely different, a region where time and space are fundamentally altered in ways we can't yet comprehend. As we ponder the mysteries of time near black holes, we're reminded of how much we still have to learn about these enigmatic objects. They challenge not just our understanding of gravity and space-time, but the very nature of reality itself. And with that, we prepare to explore yet another layer of the unknown, where the boundaries of science and imagination blur in the face of the universe's deepest secrets. Now shifting our gaze to another profound enigma, we explore the question of whether black holes are perfectly smooth or if they possess hidden structures within. At first glance, black holes seem like the ultimate simplicity in the universe's massive objects defined only by their mass, charge, and spin, as described by the no-hair theorem. But beneath this apparent simplicity lies a debate that could reshape our understanding of these cosmic phenomena. The no-hair theorem suggests that black holes are featureless, with no distinguishing characteristics beyond their three fundamental properties. This idea paints black holes as smooth, almost blank slates devoid of any internal complexity. However, this view clashes with the predictions of quantum mechanics and string theory, which hint at a far more intricate reality. Quantum mechanics tells us that even the vacuum of space is teeming with activity, filled with virtual particles popping in and out of existence. If this is true, how can the interior of a black hole remain perfectly smooth? String theory, a leading candidate for a theory of quantum gravity, proposes that black holes might have internal structures known as fuzzballs. Unlike the smooth, featureless interiors predicted by classical physics, fuzzballs are thought to be tangled, complex structures made up of strings, the fundamental building blocks of the universe according to string theory. These structures could explain how information about matter that falls into a black hole is preserved, addressing the infamous information paradox. The implications of this debate are profound. If black holes are perfectly smooth, it would reinforce the no-hair theorem and support the idea that they are the ultimate simplicity in nature. But if they have internal structures, it could revolutionize our understanding of gravity, spacetime, and the very fabric of reality. It would mean that black holes are not just cosmic vacuums but dynamic, complex entities with intricate interiors. This mystery also ties into the broader quest to unify quantum mechanics and general relativity. Black holes sit at the crossroads of these two theories, and understanding their interiors could provide the key to reconciling them. Whether black holes are smooth or structured, the answer will have far-reaching consequences for our understanding of the universe. As we ponder this question, we're reminded once again of the awe-inspiring complexity of black holes. They challenge us to rethink our assumptions and push the boundaries of science. And with that, we prepare to delve into yet another layer of the unknown, where the mysteries of black holes continue to unfold. Now turning to a fascinating question that challenges our traditional methods of observation: can black holes be detected without light? For centuries, astronomers have relied on light, whether visible, X-ray, or radio waves, to study the cosmos, but black holes by their very nature are invisible. They don't emit light or any form of electromagnetic radiation that we can directly observe. So how do we detect these elusive cosmic giants when they remain shrouded in darkness? One groundbreaking method is gravitational lensing. This phenomenon occurs when a massive object, like a black hole, warps the fabric of spacetime around it. When light from a distant star or galaxy passes near a black hole, its path is bent, creating a magnifying effect. This distortion can reveal the presence of a black hole, even if we can't see the black hole itself. Gravitational lensing has already been used to detect black holes in regions of space where traditional methods fall short, offering a powerful tool for mapping these invisible objects. Another revolutionary approach is the detection of gravitational waves. These ripples in spacetime, predicted by Einstein's theory of general relativity, are produced by cataclysmic events like the collision of two black holes. In 2015, the Laser Interferometer Gravitational Wave Observatory, or LIGO, made history by detecting gravitational waves for the first time, confirming the existence of black holes in a way that light-based observations never could. Since then, gravitational wave astronomy has opened a new window into the universe, allowing us to listen to the cosmos and uncover black holes that would otherwise remain hidden. But even with these advanced techniques, questions remain. How do we detect isolated black holes that aren't part of a binary system or near a light source to create lensing effects? Could there be black holes drifting silently through space, completely undetectable by current methods? And what about intermediate mass black holes, which are theorized to exist but have yet to be definitively observed? These unresolved questions highlight the limits of our current technology and the need for innovative approaches to uncover the full population of black holes in the universe. As we continue to refine our methods, the search for black holes without light pushes the boundaries of science and technology. It challenges us to think beyond the visible spectrum and explore new ways of observing the cosmos. And with each discovery, we come closer to unraveling the mysteries of these enigmatic objects, reminding us that sometimes the most profound truths are hidden in the darkness. Now shifting our gaze to one of the most speculative and mind-bending mysteries of all, what role might black holes play in the multiverse? The idea of a multiverse, a vast collection of parallel universes, has long fascinated scientists and science fiction enthusiasts alike. But could black holes, those enigmatic cosmic phenomena, serve as bridges or gateways between these alternate realities? This question takes us to the very edge of theoretical physics, where the boundaries of our understanding blur into the realm of possibility. One intriguing theory suggests that black holes might not be the end of matter and energy, but rather a passage to something entirely different. According to some interpretations of general relativity, the singularity at the heart of a black hole could act as a kind of cosmic tunnel connecting our universe to another. These hypothetical tunnels, known as Einstein-Rosen bridges or wormholes, have been proposed as potential shortcuts through spacetime, linking distant regions or even entirely separate universes. But here's the catch: traversing such a wormhole would require conditions that defy our current understanding of physics, including the need for exotic matter with negative energy to keep the tunnel stable. Without it, the wormhole would collapse almost instantly, making travel through it impossible. Another fascinating idea ties black holes to the concept of universe creation. Some theories propose that the extreme conditions inside a black hole could trigger the birth of an entirely new universe. In this scenario, the singularity doesn't mark the end of space-time, but rather the beginning of a new one, expanding into its own cosmos. This would mean that every black hole in our universe could be the seed of another, entirely separate universe, creating an infinite web of interconnected realities. While this idea is purely speculative, it raises profound questions about the nature of existence and the potential interconnectedness of all things. But the mysteries don't stop there. If black holes do connect to other universes, how could we ever detect or prove such a connection? The event horizon of a black hole acts as a one-way barrier, preventing any information from escaping back into our universe. This means that even if a black hole were a gateway to another reality, we would have no way of observing or interacting with it directly. The very nature of black holes makes them both tantalizing and frustrating for scientists, as they simultaneously hint at incredible possibilities and guard their secrets with impenetrable darkness. As we ponder the role of black holes in the multiverse, we're reminded of how much we still have to learn. These cosmic enigmas challenge us to rethink our understanding of space, time, and reality itself. Could black holes be the keys to unlocking the mysteries of the multiverse, or are they simply cosmic dead ends? For now, these questions remain unanswered, inviting us to dream, explore, and push the boundaries of science ever further. And as we continue to unravel the secrets of black holes, we may find that the universe or multiverse holds even more wonders than we ever imagined. Now, as we reach the final frontier of our exploration, we confront perhaps the most profound question of all: will we ever fully understand black holes? These cosmic enigmas have captivated scientists and dreamers alike for decades, yet they remain shrouded in mystery, defying our best attempts to unravel their secrets. The journey to comprehend black holes is not just a scientific challenge, it's a test of the limits of human knowledge itself. One of the greatest obstacles in understanding black holes lies in the very nature of these objects. They exist at the intersection of two of the most successful yet incompatible theories in physics: general relativity, which describes the universe on a large scale, and quantum mechanics, which governs the behavior of the very small. Black holes force these two frameworks to collide, creating paradoxes and contradictions that our current theories cannot resolve. For example, the information paradox, where information about matter falling into a black hole seems to vanish, remains one of the most stubborn puzzles in modern physics. Without a unified theory that bridges the gap between relativity and quantum mechanics, our understanding of black holes will always be incomplete. Another challenge is the sheer inaccessibility of black holes. Their event horizons act as impenetrable barriers, preventing us from observing what lies within. even the most advanced telescopes and detectors can only gather indirect evidence, such as gravitational waves or the behavior of matter swirling around the edges. This means that much of what we know, or think we know about black holes is based on theoretical models and simulations, which, while powerful, are still limited by our current understanding of the universe. Yet, despite these challenges, there is reason for hope. Advances in technology and theoretical physics are bringing us closer than ever to unlocking the secrets of black holes. The detection of gravitational waves in 2015 marked a turning point, providing a new way to observe these cosmic giants and their collisions. Meanwhile, researchers are exploring groundbreaking ideas like string theory, loop quantum gravity, and holography, which could one day provide the missing pieces of the puzzle. These efforts remind us that science is a journey, not a destination, and that every discovery brings us one step closer to the truth. But even if we do one day develop a complete theory of black holes, will we ever truly understand them? The answer may depend on what we mean by understand. Black holes challenge not only our scientific knowledge but also our philosophical perspectives. They force us to confront questions about the nature of reality, the limits of observation, and the very meaning of existence. In this sense, black holes are more than just objects of study. They are mirrors reflecting the boundaries of human curiosity and imagination. As we conclude our journey through the 30 unsolved mysteries of black holes and singularities, we're left with a sense of awe and wonder. These cosmic phenomena remind us that the universe is far stranger and more beautiful than we can imagine. And while we may never fully understand black holes, the pursuit of knowledge itself is a testament to the boundless spirit of exploration that defines us as a species. So, what do you think? Will we ever crack the code of black holes, or are some mysteries destined to remain unsolved? Share your thoughts in the comments below, and don't forget to subscribe for more deep dives into the wonders of the cosmos. Until next time, keep looking up as we bring our journey through the 30 unsolved mysteries of black holes and singularities to a close. It's impossible not to feel a profound sense of wonder. These cosmic enigmas, from the nature of singularities to the possibility of black holes as gateways to other universes, remind us just how vast and mysterious the universe truly is. Each mystery we've explored, whether it's the fate of matter falling into a black hole, the origins of supermassive black holes, or the tantalizing idea of Hawking radiation, challenges our understanding of reality and pushes the boundaries of human knowledge. Black holes are not just scientific puzzles, they are windows into the deepest questions about existence itself. They force us to confront the limits of our theories, the nature of time and space, and even the possibility of alternate realities. And while we've made incredible strides in unraveling their secrets, from detecting gravitational waves to theorizing about quantum gravity, the truth is that black holes remain as enigmatic as ever. But perhaps that's what makes them so captivating. They remind us that the universe is a place of infinite complexity and beauty, where every discovery leads to new questions. They inspire us to keep exploring, to keep questioning, and to keep dreaming. So, what do you think? Do you believe we'll one day solve the mysteries of black holes, or are some secrets of the cosmos destined to remain beyond our grasp? Let us know your thoughts in the comments below. We'd love to hear your ideas and theories. If you've enjoyed this deep dive into the wonders of black holes and singularities, don't forget to hit that subscribe button and ring the notification bell. There's so much more to explore, from the mysteries of dark matter to the birth of galaxies, and we can't wait to take you on the next cosmic adventure. Until then, keep looking up and remember, the universe is full of wonders waiting to be discovered.